let's go all the way back to our first formula for work. And remember, this was, we allowed it to be a variable force. We allowed it to be a direction that was not just the x direction. So it was less boring than 126 and more realistic. We could walk around or we could fly around in a plane. But we still had the direction of the force being the same direction as your displacement. We were just pulling in the direction we were moving, which may not always be true. We may, what about this poor guy? Not always possible or effective or something to pull in the direction that you're moving. So we would like to allow for a vector force function. So now we're going to do different, let's see, so varying force, but maybe different direction from movement. Okay, so now you're going to have a vector force, and it's going to depend on time, and then you're going to have some x of t, y of t, and z of t here. Okay, so now we want the integral over our curve of the vector force dotted with the change in direction. And that accounts for, it's the same thing that happened with this poor guy who was pulling up and wasting energy. This dot product multiplies by the cosine theta, so it doesn't account for this up motion when we only wanted right motion. It takes out the wasted work. Okay, and let's just see if we believe that this is the same as the other one. So if we think of our f of x, y, z example, and that was, we were calculating the integral f of x, y, z ds, which was supposed to be equal to f, plug in r of t, take the magnitude of r prime of t dt, right? Going from, I guess, a to b. Okay. What would be the analogous case if we were going in the same direction as our movement? Then we would just set our big F of t equal to our little f of x, y, z, which is a scalar, but we multiply by the unit vector in the direction we're moving. And then if r is movement or displacement vector, then r prime is our velocity vector. So the unit vector in the direction that we're moving is r prime of t over the magnitude of r prime of t. And if we just set that equal and plug it into this formula, let's see what happens. This is then the integral over c. We have f of x, y, z times, that's not a dot product, it's just a times, so I guess I'll take away the dot, times this unit vector in the direction that we're moving. But now we have to dot it with dr. And then dr, remember dr by dt is just r prime, so dr as a vector must be r prime of t dt. So we're dotting with r prime of t dt. And now we're really seeing the dot product, meant to highlight, not cross out, dot product of this r prime vector with itself. If you dot a vector with itself, it's just the magnitude squared, because the cosine theta is 1. So we're integrating over c, or we can write a to b now that we have a dt here. F of x, y, z, and then this is the magnitude of r prime of t squared. That's the dot product with itself. And then we still have one of the magnitudes down here, dt. So then the one down here will cancel with one of these. And we're left with the exact same formula as the other one. So if we're moving in the direction of motion, this is actually consistent with what we had before. But now we can be a little bit more general. So there's the general formula. I'll just write it out once again for clarity. I never actually wrote the full formula. So integral of f dot dr, we're just going to replace the dr with r prime of t dt, so f dot r prime of t dt.